Welcome to tutorial session 10. So in this session I'm going to cover questions on Bode plot and Nyquist plot. So in the previous weeks we have started the frequency plots. So we have covered the Bode plot in the previous session. So in this session we are going to cover majorly from Nyquist plot. So how to plot the Nyquist plot. So in the next week we will be covering how to relate Nyquist plot to the stability of the system. Okay. So I'm going to do few questions. These are assignment questions for week 10. Okay. So there are total 15 questions. So I'm going to cover a solution for each of them. So this is the first question. Consider a negative feedback closed loop system whose open loop transfer function is this. The slope in dB per octave of the high frequency asymptote in the magnitude plot of the corresponding sinusoidal transfer function is. So for the corresponding open loop transfer function, first we have to plot the Bode plot and we have to see the slope of high frequency asymptote in the magnitude plot. So in this week we have studied the shortcut, right? So how to get to the high frequency asymptote. Okay, so which is equal to minus 20 n minus m dB per decade. So this is the slope in decade. So this is the high frequency asymptote slope. Okay, so in magnitude plot. So I'm discussing the questions. So you joined recently. Okay, so I'm covering questions for the week 10 assignments. Okay, so let me ask you, do you have any doubt regarding any theory portions that have been covered in this week, so that I can go back and again briefly discuss so week 10 content. Otherwise I will continue with the questions for the assignments. Okay, think about it. I will just read the questions once again. Okay, so consider a negative feedback closed loop system whose open loop transfer function is this. The slope of the high frequency asymptote in the magnitude plot of the corresponding sinusoidal transfer function is. So in this, for the particular, this is open loop transfer function. For this particular transfer function, we have to plot the Bode plot. Okay, so we have to plot the magnitude plot and we have to see what is the slope of the high frequency asymptote. Okay, so that is how the typical like process is. But in this case, so in this week we have studied for high frequency asymptote in magnitude plot, which is equal to minus 20 n minus m dV per decade. Okay, or minus 20 n minus m dV per octave, right? So what is m? N is the number of poles and m is number of zeros. Okay, so for this particular transfer function, which is s plus 1 s square plus 12s plus 20, so you can see in the numerator s plus 1, so it has 1 0, right? So m is equal to 1. So what about number of poles? So you can see it's a second order, s square plus 12s plus 20, so it will have 2 roots. So those roots are what? Poles. Okay, so open loop poles. So the value of n is equal to 2, so you know, so what is m minus n, which is equal to 2 minus 1. Okay, just 1. So hence, so what is the slope? So in this question we have to find the slope in dV per octave. Okay, so minus 20 n minus m is 1 dV per octave. Okay, so this will be the slope for this particular transfer function. Okay, so the answer is minus 6 dV per octave. Okay, we'll also plot the magnitude plot for this GS, and you'll see. Okay, but for this question, it's already what we have studied in the theory. We are just applying here. Okay, so any doubt here for this question? Okay, you see this part. Okay, high frequency asymptote in the magnitude plot. So you have to find the slope. Okay, so simply what we know, the slope is equal to this. Okay, minus 20 n minus 1 dV per decade for the high frequency asymptote. Okay, and for this particular transfer function, m is equal to 1. So m is what? M corresponds to zeros. Okay, you see the numerator, and n corresponds to poles for the transfer function, which corresponds to the roots of the denominator. Okay, so n minus n here. Okay, this is wrong. This is n minus n. Okay, is equal to 2 minus 1. Okay, which is equal to 1. So it means the slope is minus 20 dV per octave. It's very simple. Okay, I hope there is no doubt. Okay, so let me go to the next question. So in problem 1, the corner frequencies of the sinusoidal transfer functions are. Okay, let me again write this open loop transfer function, which is s plus 1 square plus 12s plus 20. Okay, so s plus 1 divided by s square plus 12s plus 20. Okay, so let me factorize the denominator part. Okay, so s plus 1, so this denominator can be written as 2s plus 12s, sorry, 10s plus 20. Okay, so roots are what? S plus 1 divided by s plus 2 and s plus 10. Okay, so this is how the transfer function is. So I just factorize the denominator, and let me write a in the form. So from the denominator, so I'm taking 2 common and 10 common. Okay, so it looks like s plus 2 plus 1 and s plus s by 10 plus 1. Okay, so if I write it properly, I'll get p is equal to 1 by 2 by 10, 0.05. Okay, so 1 by 20 is 0.05, s plus 1 into s by 2 plus 1 and s by 10 plus 1. Okay, so I have to find the corner frequencies here. Okay, so you studied these terms, like, okay, let me write it individually, then it is more clear, though we know this. Okay, s plus 1 into 1 by s by 2 plus 1 into 1 by s by 10 plus 1. Okay, now you can see clearly, like, this part we have studied, right, for the transfer function. So I just separated all the individual components of the transfer function in this fashion here. Okay, so you know 0.05 is the constant term, s plus 1 in the numerator, it is like the slope, it is like a 0. Okay, and other two terms are s by 2 plus 1 and s by 10 plus 1. Okay, so we have to find the corner frequencies here. Okay, so also, okay, so if you remember what we have studied, transfer function of this form k. Okay, it is like st plus 1, st2 plus 1 and st3 plus 1. It is of this type, right? Okay, so how to find the corner frequencies? So in this particular, for this ps that I have written in red, so corner frequencies for this case was like 1 by t1. Okay, other corner frequency is 1 by t2 and 1 by t3. Okay, this thing we have studied, right? Corner frequency is like 1 by the time constant. Similar thing we have to do with the given transfer function. Okay, so can you tell me what are the corner frequencies? Okay, so can you relate the two transfer function written in blue and the red. Okay, constant we know, so this is constant, right? So what is omega 1?
1, 2 and 10.
1, 2 and 10. Okay, directly I have given the answer. Okay, so the corner frequencies, if you see the numerator, s into 1 plus 1. Okay, so t1 here, so I'll just write, if you just see, t1 is equal to 1. Okay, t2 is equal to 1 by 2 and t3 is equal to 1 by 10. Okay, and we are looking for corner frequencies. Okay, so the corner frequency is 1 by 1, this is 1 by t2 which is equal to 2, and omega 3 is 1 by t3 which is equal to 10. Okay, so very clearly this is 1 radian per second, so all the frequencies are in radian per second. Okay, so these are corner frequencies. One, 2 and 10. So let's see. So the first option is correct option. Okay, so any doubt in this case? So what we have studied, and we are just comparing the transfer function. Okay, I hope there is no doubt. This is also very simple. So what I have done for the given transfer function, numerator is already factorized, so I have just factorized the denominator. So two factors are s plus 2 and s plus 10. So written in the form of time constant. Okay, so for that I have taken 2 and 10 outside of the bracket. Okay, so again now my constant becomes 1 by 20, which is equal to 0.05. Okay, so I can, if I relate red and blue transfer functions, so I can get the time constant, and inverse of time constant is the corner frequencies. Okay, omega 1, omega 2 and omega 3, which is 1, 2 and 10. So any doubt in this question? Very simple. Okay, go to the next question. And problem 1, the magnitude in dB of the sinusoidal transfer function as frequency tends to 0 is. Okay, so this is the transfer function. So let me write in this form. Okay, okay, so if so you have to find the low frequency asymptote, right? Because you have to find the magnitude. Okay, so if we get the sinusoidal transfer function, which is 0, just put is equal to j omega. So this is the lengthy process that I am doing. Okay, straight away directly you can plot the, just by seeing the this GS, you can directly plot the Bode plot. Okay, magnitude plot. So that also I'll discuss in the, like, if I at the last of this question. Okay, so what is the magnitude here? Okay, so we are looking for low frequency asymptote. Okay, in magnitude plot, right? So what happens in this, in that case? Okay, we neglect the omega term because omega is very small, it is close to 0, low frequency region. Okay, so if we neglect that, so what we get, so we are left with 0.05, right? If we neglect omega square terms with respect to 1, because omega is very small. Okay, then omega by 2 whole square and omega by 10 by whole square is also very small. Okay, as compared to 1, so it is like 1 into 1 into 1. Okay, So I'm directly writing this 0.05. So this is the magnitude. Okay, so in dB we have to find out, right? So what we do, we take the 20 log of 0.05, okay, to get in dB. Okay, this is in dB. Okay, so this is, so this you have to find out 20 log 0.05. Okay, so what is that? So I'm getting minus 26.02. Okay, so this is in dB. Okay, so low frequency asymptote in magnitude is minus 26 dB. Okay, so that is what is asked here. The magnitude of the sinusoidal transfer function as frequency tends to 0. Okay, so this low frequency asymptote is at low, this is at very low omega. For that we are getting a constant magnitude. In dB it is minus 26 dB. Okay, so this is the correct answer. Okay, so any doubt in this question? See, straight away, you know, if you write the transfer function in this form, okay, directly you know, if you write the, without even going to this step, okay, so you'll know that with respect to 1, s term is very very small, so you'll be left only with 0.05, that is the constant term. Okay, so this constant term, and directly you take the 20 log of k, you'll get the this magnitude of sinusoidal transfer function in low frequency region. Okay, we have done many questions and directly we can write. So any doubt in this particular question? Very simple. Okay, so I'll go to the next question. In problem 1, the phase of the sinusoidal transfer function as frequency tends to infinity. Okay, so I'm writing 0.05 is plus 1 is plus 2 is plus 10 plus 1. Okay, so this is the transfer function, and if you find out the sinusoidal transfer function, replace with this with j omega. Okay, and we have to find the angle. Okay, so the phase of this is, okay, phase of 0.05 is 0. Okay, and plus tan inverse imaginary by real, so imaginary part is, if you see the numerator, okay, imaginary part is omega and real part is 1. Okay, and if you go to the denominator, we'll get tan inverse of imaginary part is omega by 2 and the real part is 1 minus tan inverse of omega by 10 by 1, which is equal to omega by 10. Okay, so this is the phase, okay, for this particular transfer function. Okay, and what you have to find out? You have to find out the phase as frequency tends to infinity, as omega tends to infinity. Okay, so what is tan inverse of infinity? So if you put this, okay, so this is 90 minus 90 minus 90. You know tan inverse of infinity is equal to 90, right? Okay, so the phase of the sinusoidal transfer function is minus 90 as omega tends to infinity. Okay, this is also very simple. So the answer is minus 90. Okay, so any doubt in this question? So we are finding out the phase. So you know how to find the phase. Okay. So individually for each numerator and denominator part, I have written the phase. Okay. And at infinity, tan inverse of infinity is equal to 90 degree, right? So 2 90 90 cancel, and we are left with minus 90 degree. So that is the phase of this transfer function. Very simple question. I hope everything is clear in this question. Okay, we'll go to this problem. In problem 1, the slope of the low frequency asymptote in magnitude plot of sinusoidal transfer function is. So we have to find the slope. Okay, so already we found out. So what is the magnitude you see here? So let me just copy this. Okay, so we have found out the magnitude at low frequency region in the magnitude plot. Okay, so can we so this is the magnitude. Okay, so looking at this magnitude, so we are concerned about the low frequency region. Okay, so what can you say? Just look at this magnitude. What can you comment on the slope with respect to the frequency? Okay, can I say this low frequency asymptote? So you know corner frequency, we know 1, 2 and 10, right? So I'm talking about frequencies less than 1 radian per second. Okay, so we know the magnitude is equal to 0.05. Okay, so 0.05 is not varying with respect to omega, right? It is constant. So when the magnitude is constant, what is the slope?
0 dB per decade.
Correct. So 0 dB per decade or 0 dB per octave. Getting it? Simple. We'll also plot the magnitude plot, but what we have studied just we are applying here. Okay. So it is asking for low frequency asymptote slope. Okay. So it is we are assuming that low frequency asymptote slope means frequencies which are lesser than 1 radian per second. Okay. If you see that region, the magnitude is constant, which is equal to 0.05, and in dB it is minus 26 dB. Okay, so it's not varying with frequency. So the slope is constant and is equal to 0. Okay, any doubt in this question? Okay, go to the next question. Let me check. Okay, so this is the right time to plot the magnitude plot. Okay, so GS is equal to 0.05 is plus 1 pi 2 plus 1 pi 10 plus 1. Okay, so let's plot the magnitude plot here. Okay, so this is in dB. Okay, so we have 3 corner frequencies, right? So 1 radian per second, 2 radian per second. So let me, this 2 radians per second and 10 radian per second. Okay, so let me again confirm. Okay, yeah, s plus 10, s plus 2 and s plus 10. Okay, so we have to plot the magnitude plot. Okay, so below 1 corner frequencies, so just remember like what we have studied. What is the contribution for these type of components? Ts plus 1. Okay, let me say T1 s plus 1 and 1 by T2 S plus 1. Okay, so below the corner frequencies, so what is its effect? Okay, so let me just see the effect of this first component Ts plus 1. Okay, so you know, if you write the magnitude, let's suppose only we have, let me consider it. So I'll not go back to the notes, just here. Okay, let me consider a transfer function. Okay, let me call it P1s, which is equal to T1s plus 1. Okay, just this transfer function. Okay, so if you see the sinusoidal transfer function, it is 1 plus j omega into T1. Okay, or you can write j omega T1. Okay, so what is its magnitude? This is its magnitude, omega T1 square. Okay, so in low frequency regions, okay, omega is very small. Okay, so omega is very small, so what we used to do, what we used to assume, magnitude is equal to 1. Okay, so this is in, or I'll call this low frequency asymptote. Okay, okay, so the magnitude is equal to 1, and if you take in 20 dB, so what is the magnitude when you take in dB? 20 log of 1, which is equal to 0 dB, right? So below corner frequency, it is contributing 0 dB in the magnitude plot. Similarly, if you consider this function 1 by T2 S plus 1, okay, directly if I write the magnitude, what I will get? 1 by 1 plus omega T2 square. Okay, similarly for the low frequency asymptote, what you do? Omega is very small. Okay, let me just, okay, omega is very small, so you neglect omega if you compare it with 1. Okay, so magnitude is again equal to 1. Okay, so in dB, what is the magnitude? Again in this case also, if you take in dB, 20 log of 1 is equal to 0, right? If you see these two functions. Okay, so numerator part and denominator part. Okay, below their corner frequencies, the contribution in the magnitude plot is equal to 0 dB, right? So this is what we have to see here. Okay, so if you see the numerator part S plus 1 and denominator part S plus 2 plus 1 and S by 10 plus 1, so the contribution below their corner frequencies is equal to 0, right? 0 dB. So the only contribution we have is 0.05. That already we have seen in the previous question, this question itself. Low frequency asymptote. So the region especially below 1 radian per second. Okay, so which will be equal to minus 26, right? So okay, so this is minus 26 dB. Okay, so after 1, what is happening? Okay, so after 1, this 1 comes into picture. Okay, so I'm just plotting approximate plot. Okay, S plus 1. Okay, so what it will do? Okay, so it will have 20 log of omega component. If you refer to the theory, 20 log of omega component. Okay, so other two denominator parts will not contribute anything still, because if you see 1 to 2 region, okay, so only contribution is by, okay, let me write specifically, if you consider omega less than 1, okay, GS is 0.05. okay, so it's like magnitude I'm writing. Okay, let me. Okay, from omega 1 to 2. So magnitude will be due to 0.05 into s plus 1. Okay. So let me write in terms of s itself. And from 2 to 10, I'll have 0.05 into s plus 1 and s pi 2 plus 1. Okay. Write it separately. Okay. And frequency is greater than 10, so all the components will contribute. Okay. Okay, 4 regions, right? 1, 2, so 3 and 4 regions. Okay, so in first region, only 0.05 is contributing. Okay, the contribution is minus 26 dB that we have calculated. That's why I'm writing. Okay, so in region 2, from 1 to 2, what is happening? 0.05 and s plus 1 will contribute. So what is the contribution by s plus 1? So the magnitude will increase, right? By the slope of plus 20 dB per decade. Okay, so just like this. Okay, so this is approximate plot. Okay, I'm not writing what is the magnitude at omega equal to 2. Okay, then at omega equal to 2, what is happening? Okay, so s plus 2 plus 1 will again start contributing. Okay, so let me add this also. So you have to see this effects also. Okay, so again what it will do, it will flatten the curve here up to omega equal to 10. Okay, at omega equal to 10, what will happen? This will also come into picture. Okay, then what will be the slope? Again it will be minus 20 dB per decade. Okay, so let me write the slopes here. This is 0 dB per decade. Okay, this is plus 20 dB per decade. This is again, it becomes 0 dB per decade, and this is minus 20 dB per decade. Okay, and in the first question itself, okay, this we have calculated, right? This slope already we have calculated. Okay, and this is asked in question, both the slopes. Okay, so what these slopes that I have highlighted in orange color. Okay, so one is high frequency asymptote, okay, and the other one is low frequency asymptote, right? And from the formula minus 20 n minus m per decade, we have calculated the slope for high frequency asymptote. So if you see the first question, okay, this is the first question. So what? So our answer was minus 20 dB per octave. Sorry, this is per octave. Answer is wrong. So it should be 6. Okay, so we are talking in octave, so it should be 6. Okay, 6 dB per octave, right? Or minus 20 dB per decade, because finally we are drawing a decade. Okay, so you can see, so already we got the slope, right? From the formula we got the slope, but you see the final magnitude plot. Okay, here also you can see we are getting minus 20 dB per decade. Okay, so this is the entire plot. Okay, so I have not calculated this frequency, what is this, okay, that you can calculate. But this is how the plot will look like. So any question?
So like in the frequency 1 to 2, why is it plus 20 dB?
Why not, like, okay, you can write in octave, it can be plus 6 dB octave, because of this S+1 contribution. You see this term. So what is the contribution, okay, in the low frequency and in the high frequency? High frequency means after corner frequency. So if you just individually plot the magnitude plot for this, so what you will get, you're getting 0 dB, right? And at
Yes.
corner frequency, your magnitude will increase like this, right? Okay, so this is the corner frequency, like 1 by T1, this is 0 dB. Okay, so that this is like 20 log of omega. Okay, and what was the slope we have seen in the theory? This is 20 dB per decade. Okay, the slope I am writing, I'm not writing anything. Like slope will be 20 dB per decade or plus 6 dB per octave. Okay, you see, just see this. Okay, this is for T1s plus 1 itself. And for this, if you plot the magnitude plot, what you will get, 0 dB, then your slope will decrease. Okay, so this is 0 dB. Okay, this is what, minus 20 dB per decade. Okay, so that's what I have drawn here. Okay, I'm not drawn like full, just approximate plot here. Okay,
Okay, sir. Okay.
if you just do as the professor have done, you'll get to the same result. Okay, we are actually adding in any range you take 2 to 10, you see, you just add all the magnitudes, you'll get this. Okay.
Yes.
Okay. So we are also confirming by drawing the magnitude plot. Okay, whatever we have previously found out. Okay, and I think we can also find out the, I think, not required phase plot. Okay. So any doubt you have in this plot, magnitude plot? Once again, I'm not getting. Okay, so any doubt you have in this? Okay, it's very interesting. You'll use this plot. Okay, so in problem 1, we have to find the static position error constant. Okay, so you know the definition of static position error constant? So what is that? Okay, so this is open loop transfer function. Okay, so this is the definition of static error constant. Okay, so one way is, because let's use, because since we have learned the Bode plot, so yeah, so we'll be using this Bode plot to find out the static error constant. Okay, this we know, and we have to find KPE. Okay, so S tends to 0, so GSHS you have to find out, which is equal to 1. Okay, so basically we have to find out this. Okay, so can you tell me which region it's talking about? Because S is tending to 0, that means low frequency region, right? or omega equal to, because for the sinusoidal we are putting s equal to j omega, and j omega is very small. S is small means j omega, omega is very small. Okay, so we have to find gs hs when s tends to 0. So this is the basic definition. You see this? Okay, so what is that region? Can we say this region is same thing as here also? You're finding the magnitude at g0, right? Is h is equal to 1. Okay, so this is also true, right? By looking at the Bode plot. So can we not say Kp is same thing? This you have to find out. Okay, so Kp is like, let's not go in dB. Let's find out without dB, like original constant. So what was that, which was equal to 0.05, right? So in dB it is minus 26 dB. Okay, but if you take the absolute value, what is that value? Which is equal to 0.05. Okay, so this is how we find the position error constant. You see the definition of that. Position error Kp is equal to limit s tends to 0 gs into hs. Okay, hs we know it's a unity feedback, so hs is equal to 1. Okay, so only we are left with gs. Okay, and if you put the limits, you'll get g of 0. Okay, g of 0 is with what? Low frequency, right? So here also we have plotted the magnitude here. So at low frequency, what we are getting? We are getting at low frequency 0.05. Okay, so what is the conventional method, like what we have studied in the, so its answer is 0.05. So how to find, what we used to do? Kp is limit s tends to 0. So for our case it is 0.05 s plus 1. Okay, s plus s by 2 plus 1 and s by 10 plus 1. So we have to find out this, right? And put the limit, what you'll get? You'll get, if you put the limit, 0.05. Okay, this we are just seeing from the Bode plot. Okay, s equal to 0 means low frequency region. We have to find out the value of g of s at low frequency. Okay, so what you do, you just see the Bode plot at low frequency, and in this particular question we are getting 0.05. Okay, if we don't take the magnitude in dB. I hope this we know, right? This portion we know. Okay, but how to find from the Bode plot? How to find the Kp from Bode plot, that I have shown you. Okay, you can refer to this also. Any doubt in this question? Okay, also if you see the low frequency region, okay, so the magnitude is 0 dB per decade. Okay, so you can also comment on the type of the system. Okay, so just by looking at the slope of low frequency asymptote, you can comment on the type of the system. So here the slope is 0 dB per decade. Okay, so we can say the type of system is what? 0. Okay, and this transfer function we know. The transfer function is this 0.05 into s plus 1, s by 2 plus 1 and s by 10 plus 1. Okay, so we can also confirm just by looking at the Bode plot also. Okay, because let's suppose we have this term also, s. If suppose we have this s term, then what you will see is zero frequency there, then the slope will be this, like this slope will be minus 20. So let me also draw separately, okay, just to get the clarity. Bode plot for this g of, write in different color. Which color? Okay. Okay. So g of s is 0.05. Okay. So if I plot the Bode plot for this. Okay. So approximately I'm drawing the Bode plot. So you just see the low frequency region. So what you'll get? Okay. So you'll get this. Okay. So let me write the slope. So this 20 dB per decade. This is 0 dB per decade. This is minus 20 dB per decade, and this will be minus 40 dB per decade. Okay. This is how the slope will look like. Okay, so this is in magnitude. So just if we look at this, okay, low frequency asymptote, okay, you know the slope is minus 20 dB per decade. Okay, so we can comment that because it's minus 20 dB per decade, we have a type 1 system. Type 1 system means this S, we have a S term. Okay, the previous case it is equal to 0 dB per decade. That's why we don't have any S term. That's why it's a type 0 system. Okay, let me again here highlight and say it's a type 0 system, and here it is type 1 system. Okay, so for type 2 system, what you will have initial slope to be minus 40 dB per decade. Okay, then you will have S squared term. Okay, so our question is regarding this. So KPE position error constant, but just by looking at the Bode plot we have found out, which is equal to 0.05. Okay, and also just by looking at the plot we can also comment on the type of the system. Okay, so here the type of system is 0 dB per decade. So also I have shown for the type 1 system. So I just change the transfer function and include it 1 by S term, and what will be its impact on the Bode plot that I have shown here. Okay, and also if you try to find out the slope of high frequency asymptote, okay, the formula is what? Minus 20 n minus m dB per decade, right? This is the formula. So now if you see here, n is what? 3, right? So now the number of poles are equal to 3 and 0 is still 1. So if you find n minus m, which will be 2. Okay, so if you do that, what you'll get? This is minus 40 dB per decade. Okay, slope of high frequency asymptote in magnitude. Okay, so can we confirm from the graph? You see here this. Okay, because of that S we got minus 20 dV per decay. Okay. Okay, I hope this is clear. Any doubt in this question? So additionally we have done some things. Okay. Okay, let me go to the next question. It says, in problem 1, the steady state error of the closed loop system's output to the unit step reference input is. So anyway, we have already found out that. Okay, so what is error? Error is 1 plus KPE. Okay, this was the formula for this unit step reference, if you remember that. So what is that? 1 by 1 plus 0.05. So what is, we'll get 0.95. Okay, this is the steady state error. Okay, if you don't remember this also, so what we know, error is equal to what? Limit of s tends to 0 s into es. Okay, so what was es? Es is rs into 1 plus gshs, open loop transfer function, gshs, right? So let's calculate that. So rs is a unit step, so that's already we know. So rs is 1 by s, 1 plus gshs, which is 0.05. Okay, so s plus 1, s by 2 plus 1, and s by 10 plus 1. Okay, so what you'll get? Okay, you'll get this 1 by 1 plus limit of s tends to 0, 0.05. Okay, I'm just writing so that you understand how I'm writing formula directly 1 by. So this term is what? This term is kp. Just now we have calculated it. Okay, that's why I'm writing finally 1 plus kpe. Okay, so I'm getting from here, right? Which is 0.95. So any doubt in this case? So only for the type 0 system you will get this. Okay, that already we have discussed when we are discussing the how to find out the various error constants. Okay, so any doubt in this case? Okay, I'll go to this one. The plot of the real part of sinusoidal transfer function and its imaginary part as frequency is varied is, so this is Nyquist plot. Okay, definition of Nyquist plot. So what we'll do, we'll plot the g of we'll plot g of j omega, okay, in complex plane or GES plane. Okay, when omega is varied from 0 to infinity. Okay, let me write this. Okay, so it will have real part, okay, and imaginary part. Okay, so this is what this is called as Nyquist plot. Okay, I hope there is no doubt in this. So in this question, which one of the following statement is true about the Nyquist plot of factor s plus 2 as the frequency is varied from 0 to infinity? Okay, so you have to plot the Nyquist plot, in which quadrant it is lying. Okay, so what is the sinusoidal transfer function? 2 plus, okay, let me write like this, j omega plus 2. Okay, so what is its real part? So let me say real part is 2 and imaginary part is, in this case, okay, omega. Okay, let me change this to blue. Okay, this you know. And also if you find what is the magnitude of p of j omega is 2 square plus omega square. Okay, if you try to find angle is equal to tan inverse of omega by 2. Okay, that we already know, and we have to plot this. Okay, so let's take the frequencies at we'll take frequency omega equal to 0 and omega equal to infinity. Okay, that, let's see what are the values. So we have to find real part. Okay, I'm writing imaginary part.
Sir, isn't it 2 square plus omega square?
2 square, correct, sorry. So this is 2 square plus omega square, correct. Okay, I think everything is correct now. Square plus, okay, so real part omega, real part imaginary part, magnitude and angle. Okay, so let's find out omega equal to 0. Okay, so what is the real part here? You see, real part is always equal to 2. It's not varying with frequency, correct? Okay, and if you see imaginary part at omega equal to 0, it is equal to 0. And what is the magnitude? 2 square root of 2 square, which is also equal to 2. Okay, and angle is equal to 0 degree. Okay, just see whether you are able to fill this table or not. Okay, at omega equal to 0, real part is 2. Okay, so this is real, which is equal to 2, or at omega equal to 0. Okay, and when you talk about imaginary part, this is imaginary part. Okay, so at omega equal to 0, this is equal to 0. Okay, and you know, magnitude is what? Root of imaginary part plus real part. Okay, so this is equal to 2, and angle is tan inverse omega by 2. Omega is equal to 0, then your phase is also equal to 0. Okay, this is very easy. So at infinity, so let's find out at infinity. So real part is what? It will be equal to 2, right? It's constant, it's not varying with frequency. So again, it is equal to 2. Okay, and if you see the imaginary part, that is also equal to infinity, right? At omega equal to infinity, imaginary part is equal to infinity. And what is the magnitude? Root of 2 square plus infinity square, which is infinity again, right? And if you see the phase, tan inverse of infinity by 2, or tan inverse of infinity, which is equal to 90 degree, right? So let's just by taking these 2 points, let's plot the Nyquist plot. Okay, so this is G of S plane. Okay, okay, so first is at omega equal to 0, This is 2. Okay, imaginary part is equal to 0, real part is 2, and the angle is equal to 0. And if you see at infinity what is happening, real part is still 2, but imaginary part is equal to infinity. Okay, so how your Nyquist plot will look like? It will be looking like this. Okay, so this is at omega tending to infinity, and this is at omega tending to 0. Okay, so it's a straight line. Okay, so this is the Nyquist plot. Okay, so just by plotting 2 points at omega equal to 0 and omega equal to infinity, you know. Okay, and as omega is tending to infinity, you'll see the phase is also will tend to infinity, right? Okay, so our question is, which one of the following statement is true? Okay, so first statement is it would always lie in the first quadrant of the complex plane. Correct, right? So this is the plot. So it's always lying in the first quadrant, right? So this is true. First quadrant of the complex plane. Second is it would always lie in the second. No, it's false. Third, fourth. Okay. So any doubt in this question? Okay, how to plot the Nyquist plot? That is already we have seen. Okay, in this, for this particular case, s plus 2, we are getting this Nyquist plot starting from 2 and going to infinity in the first quadrant. Okay, and the real part is not changing with respect to omega. It's always staying constant. Okay, because if you look at this function also, real part is not a function of omega, it's constant, but your imaginary part is. Okay, that's why it's changing from 0 to infinity. Okay, and if you see the angle, this is 0. Okay, so this is like omega, it is making 0 degree, and you know, at as you go infinity, it will be, this angle will be tending to 90 degree. Okay, so that's what this 90 degree is. Okay, so any doubt in this question? Question 9. Okay, we go to the next question then. A frequency is varied from 0 to infinity. The Nyquist plot of 1 by s plus 4 is a semicircle whose radius is. Okay, we already know the Nyquist plot is semicircle and we have to find the radius. Okay. So again, same real part, imaginary part, magnitude and phase. Let's find out, and again let's plot it. Same procedure that we have done for the previous question, we will be repeating for this question. Okay. How we can write this? Okay. So what I have done, so just one step. So let me write it here. Multiply numerator and denominator by 4 minus j omega. Okay, so you'll get this. Okay, so real part of p of j omega is 4 by omega plus 4 square. Okay, which will be always positive. Okay, you see, as the omega is very real part is always positive because we have in the denominator omega square. So imaginary part is equal to minus omega, so I'm not writing j. Okay, minus omega by omega plus omega square by 4 square. So if you see, real part is always positive, imaginary part is always negative because omega is ranging from 0 to infinity. Okay, which quadrant we are talking about when real part is positive, imaginary part is negative? Which quadrant is that? Can you answer it? Real part is always positive. Which quadrant?
Fourth quadrant.
Correct. Fourth quadrant, right? So we'll see. So this semicircle will be in the fourth quadrant. Okay. Okay. So magnitude. Okay. So what is the magnitude for this? I'm writing some mistakes there. Okay. So this is the magnitude 1 by omega square plus 4 square. Okay. And what is the angle? Okay, minus tan inverse of omega by 4. Okay. So let's see. Again, we can find at different frequencies. Okay. So at this is omega, this is real part, this is imaginary part, magnitude and angle. Okay. So at 0, omega equal to 0, what we have? If you see the real part, 4 by omega square plus 4 square. So what you'll get? If you put omega equal to 0, you'll get 4 by 4 square, which is 1 by 4, right? So 1 by 4, which is equal to 0.25. Okay. Are you able to get why the real part is 1 by 4? Okay. Omega equal to 0. Just see this and put omega equal to 0. You'll get 1 by 4. Okay. So that's what I have written here. And if you see the imaginary part in the numerator, you have omega. Okay. So that's why the imaginary part will be equal to 0. Okay. And if you find the magnitude will again will get 1 by 4. Okay, because your imaginary part is equal to 0. And what is the phase? Phase is 0. Okay, so any doubt in this for omega equal to 0 for this table? Very simple. Okay, let's find at omega equal to 4. Okay, because it's a semicircle, right? We already know. Okay, let's first find at infinity. So what is the real part? Real part is 4 by infinity square plus 4 square, which will be equal to 0. Correct?
Yes, sir.
Okay. And if you see the imaginary part, which what you'll get? Omega minus omega by omega square plus 4 square. Okay. So it will be like minus 1 by omega. So minus 1 by omega, if you put infinity, so you'll get minus 1 by infinity. 0. Right? So you see this part. So let's first see the denominator, right? Omega square plus omega square plus 4 square. So since omega is very, very large as compared to 4 square, so I can write the denominator as 4 omega square. Okay. So I'll get this. Okay. This is like approximation. Okay. So I've neglected 4 square as compared to omega square. Okay. And here what I will get again, minus 1 by omega. Okay, that's what I'm doing here. Now if I put omega equal to infinity, what I will get? 0. and if you find the magnitude, you'll get 0. And what is the phase tan inverse of omega? You'll get 90 degree, which is minus 90. Okay, from here also you can see imaginary part is negative. Okay, minus 1 by omega. Okay, so 1 by omega is very small because omega is very large, but still it's a minus of some small number. Okay, so what you're getting is 0, like real part is also very small. Okay, it's like small plus minus j of some small value. Okay, let me call it a minus jb you are getting, and a and b are very small, but if you see a minus jb is what? Okay, still in the fourth quadrant. Okay, so tan inverse of b by a we are finding out. Okay, so I'm just confusing it. Okay, so let's say we have the formula, right, to calculate the phase tan inverse of omega by 4. Okay, just put omega equal to infinity. What you'll get? 90 degree, and minus of 90 you'll get if you put here. Okay, so we got this. Okay, so let's plot the semicircle. Okay, we'll also find that omega equal to 4, but we have some points. Okay, so this is complex plane. Okay, so we have the information for 2 points. One is real at omega equal to 0, 1 by 4. Okay, this is at 1 by 4. Angle is equal to 0 degree, and at infinity we have 0 0 at origin. So these 2 points we know. So that omega tending to 0. Okay, but we know it's a semicircle. Okay, so let's also find at omega equal to 4. So at omega equal to 4, what is the real part? Okay. Okay, so real part is what? So now I am putting 4. Okay, so it's like 4 by omega square is what? 4 square plus 4 square, right? Which will be 4 into 2 into 4 square. So it will be this 2 into 4 is 8. Okay, so I'll get 1 by 8. Okay, so I have calculated the real part. So let me just put this down. So for the imaginary part, again the same thing. So it is minus, if you see the imaginary part, minus 4. Okay, 4 square plus 4 square, right? So what again it is? 2 into 4 square minus 8. Okay, so and what is the magnitude? Real part plus imaginary, it's like 1 by 8 square plus 1 by 8 square, right? It will be 2 by 8 square. Okay, and 2 by 8 square is why root 2 by 8 something it will be, if I am doing everything correct. Okay, so this will be the magnitude. And what is the angle? If you put angle directly, I will write the formula. Omega is 4 by 4. Okay, tan inverse of 1 is what? 45 degree, and we have minus sign, so minus 45 degree. Okay, So the real part is 1 by 8, imaginary part is also 1 by minus 1 by 8, and the magnitude is root 2 by 8. Okay, so what is that point here? Real part and imaginary part both is 1 by 8. So here, okay, so this, okay, this, let's say this is 1 by 8 minus 1 by 8, right? J minus j by 8, and here we have 1 by 8. Okay, this point is at omega equal to 4. Okay, just now we have calculated it, and this angle also we have calculated, minus 45. Okay, okay, so also in the theory you have studied, right? This will be a semicircle. It's already in the question, it's given. Okay, it's like a semicircle. So it's not looking like semicircle, but let's assume. Okay, this is a semicircle. It's center at 1 by 8. Okay, and what we have to find out? We have to find out the radius of this semicircle. What is the radius? Can you tell me the radius by looking at this? You just find this. This is the radius, right? 1 by 8. Correct? So this is the radius. Okay, which is 1 by 8. Simple. So answer for this question is 1 by 8. Like 1 by 4 is 0.25. 0.25 divided by 2 is 0.125. Okay. So already in the question it's given that it's a semicircle. What we needed to find out is at omega equal to 2, omega equal to 4, what is the real and imaginary part? Okay. So this distance is again we have calculated, which is 2 by 8. Though it's not useful. Okay. Angle is minus 45, but we know. Okay. By just calculating the values at 3 omegas, we are able to capture the image, okay, of the Nyquist plot. Okay, so any doubt in this question, how we got to this Nyquist plot and other things we're not getting? Okay, so at 3 points we have calculated the values for the p of j omega, different p of j omega. Okay. Okay. Let's go to the next question then. Okay, this is, yes.
Like why do you take only 4 as omega value?
Because that is the corner frequency, right?
Yes.
You can take other values also. Okay, you will get somewhere here, like since we wanted to find again this is like how to say this. Okay, so one is like it's a corner frequency that's readily available, and it's all about experience. Like if you see the what is the equation for the semicircle. Okay, so I mean it's about experience. Like one reason is like corner frequency, that is like directly looking at
Yes,
s plus 4 I can know. Other is like I'll get the equation of circle. That two information that's also I don't know, because I know the type of a transfer function and where I can get the semicircle, That's why I'm just finding it s equal to 4. Okay, other than that, I don't have any information.
Yes,
So
I
let's,
understand.
yeah. Okay. So this is very simple, like, okay. So we have to plot the Nyquist plot of E of minus, just by looking at this, the magnitude of this function is always equal to 1, right? So this is like uh, in the form of R of E of j theta, right? Some function like P of theta, Euler's form. Okay. So here R is the magnitude, the radius of the circle. Okay. Okay. In this case, what you can write here, sine of, okay, let's first find the sinusoidal transfer function, which is this E of minus j 2 omega. Okay. Which is cos of 2 omega minus of j sine 2 omega. Okay, from here it's very easy, like if you don't know like its magnitude, what is its magnitude and what is its phase, but you know this E of minus j2 omega is equal to cos 2 omega minus j of sine 2 omega. Okay, actually this is equal to plus, and we have here minus of here. Okay, let me write it properly. So cos of 2, this is minus 2 omega plus j of sine 2 omega. So that's why I'm writing cos of 2 omega minus of j sine 2 omega. Okay. So what is the magnitude? Magnitude is real parts root of real part square plus imaginary part square. Okay. So this is what is the magnitude. If I write in this term, you'll get cos square 2 omega plus sine square, which is it is equal to 1. Okay. And directly you can comment on the phase also. The phase is equal to minus of 2 omega. Okay. What is the phase? If you go by this, so you'll get 10 inverse of real part is minus sine 2 omega, and the sorry, imaginary part is minus sine 2 omega, and real part is cos of 2 omega. Okay. So let's take minus outside. So it will be, that is equal to tan of 2 omega, which is equal to minus 2 omega. Once again, I'll just, okay, sorry for the interruption. So the magnitude and the phase we know. Okay. So, and its plot is this. Okay. Okay. So since P of S is, if you see, what is its magnitude? Magnitude is equal to the radius. So in our case, magnitude is equal to 1. So the radius of this will be equal to 1. Okay. So this is the plot of E of minus j omega. Okay. So this will be the Nyquist plot. Okay. This is real part and this is imaginary part. So already we have covered this. This is G of S plane. For different omegas, you will get this. Okay. So the answer is 1. I think this is very straightforward. Already that's discussed in theory part also. Okay. For this function, for delay function. Okay. So 12 is, which one of the following statement is true about the Nyquist plot of factor as the frequency is varied from 0 to infinity? Okay. Again, we have to follow the same procedure. So this is 4s plus 2. Okay. So let's put s equal to j omega. So what you'll get 2 minus, so j square is minus 1, right? So you'll get this. Four of omega. Okay. So real part is 2 minus omega square, and the imaginary part is 4 omega. Okay. So you can see if you have omega value which is less than 2, root 2. For omega less than root 2, you will get this real part to be positive. For omega greater than root 2, you will get real part to be negative. Okay, that you will see in the Nyquist plot. And for the imaginary part, you can see it's always positive because omega is, you're varying omega from 0 to infinity. Okay, it's always positive. Okay, let's see the magnitude here. Okay, so this is the magnitude, and angle is tan inverse of 4 omega by 2 minus omega square. Okay, so different, let's put values on the table. Okay, so at omega equal to 0, so what is the real part? You see 2 minus 0 square, right? So it will be equal to 0, right? And what is the imaginary term? Imaginary term is 4 into 0. Sorry, real part is equal to 2. Okay, 2 minus 0 square. And what is the magnitude? Magnitude is again equal to 2. Okay, and the phase is equal to 0 degree. So any doubt in this case? Okay, so also let's find at 2 also. Okay, omega equal to 2, not 2, root 2, because the real part becomes 0 at that point. Okay, so what is the real part here? If I put omega equal to root 2, 2 minus root 2 square, so the real part becomes 0. And what is imaginary part? 4 into root 2. Okay, the magnitude will be equal to 4 into root 2. Okay, and let's see what is the angle at root 2. 4 into root 2, so 2 minus root 2 square. So if you see, the denominator will become 0, and so tan inverse of what you will get? Infinity, right? So this is like tan inverse of infinity. Yes, tan inverse of infinity, which is equal to 90 degree. Okay. So any doubt in the second part where omega is equal to root 2. Real part becomes 0, imaginary part is equal to 4 into root 2. Okay, and the magnitude is real square plus real part square plus imaginary part square, then whole of square root. Okay, so that's why it's 4 root 2. And if you take tan inverse, so the denominator becomes 0, so that's why tan inverse of infinity is equal to 90 degree. Okay, so and at infinity, let's check at infinity. What is the real part? Two minus omega square. Okay, so it's like minus 2 minus infinity square is minus infinity, right? This, see this part. Okay, we are putting omega equal to infinity, so it will be minus infinity. And what about the imaginary part? Same, 4 into omega. This is plus infinity, right? Magnitude is infinity. Okay, so let's see the angles. So what are the angles you are getting? So can I just use this tan inverse 4 omega? Okay, so omega square is very large as compared to 2. Okay, so I can neglect 2, right? So I'll get this. So I will take minus outside, so I'll get minus tan inverse of 4 by omega square. Okay, so yeah, then I'm cancelling omega, so I'm getting this 4 by omega. So if I put omega equal to infinity, what I will get? This term will be infinity, right? So minus of tan inverse of infinity is minus 90. Okay, so again let's see what is the real part. 2 minus omega square, and omega is infinity. Okay, but you see you'll get negative infinity, right? Because it's negative, right? This portion. And in the imaginary part,
Sir, omega tends to infinity, tan inverse of 0.
okay, yeah. Okay, correct. So as omega tends to infinity, sorry, this will be equal to 0. Correct. So let's put that. This will be 0 degree. Correct. 0 degree, or you can say 180 degree. It's a negative. We'll say plus 180 degree because of this sign. Okay, you see this, why I'm saying 180 degree. Okay, because it's in second quadrant, like you see this is in the second quadrant, so that's why I'm saying the angle is plus 180 degree. Okay, so once I plot the Nyquist plot, it will be clear. Okay, so I got 3 points here. So let's plot the Nyquist plot. Okay, so what is the first point? Real 2. Okay, this point here. Okay, and the other point is at omega equal to root 2, I'm getting real part equal to 0 and imaginary part, it's called somewhere here. Okay, so this is 2 and this is j of 4 root 2. Okay, because you see this part, real part is equal to 0 and imaginary part is this. Okay, and the angle is plus 90 degree. This also is fine. Okay, because if you see this angle is 90 degree. Okay, And the last point I am getting is infinity minus infinity. Okay, so somewhere here at this point. Okay, so how this will look like? So start from here, it will go into the second quadrant. Somewhere here. So angle, if you see at the infinity, it will make equal to 180 degree. I hope I have calculated magnitude correct for the infinity part. Exactly, this is correct. Angle is also. So this is the plot, Nyquist plot. Okay. So let me mark the frequencies. This is at omega equal to 0. This is at omega equal to 2 root 2, sorry, 2, 2. And this is at omega tending to infinity. Okay. So this is the Nyquist plot. This is not the exact plot. Okay. But what is the function? Okay. So we have to find out in which quadrant it's lying. Okay. So you know lying in the first and second quadrant. Okay. So to let's see the first option. It would always lie in the fourth and first quadrant of the complex. So this is wrong. Second option is it would always lie in the first and second quadrant of the complex plane. Okay, this is correct, right? It's lying in the first and second quadrant, right? I'm seeing the magnitude as well as the angle. Okay, so just by seeing 3 points. Okay, and the third option is incorrect, which says lies in second and third quadrant. The last option is third and fourth. So any doubt in this? We have plotted the Nyquist plot. Okay, it starts from first quadrant, the real axis, and then it goes to the second quadrant. Okay, in the second quadrant at omega equal to infinity, the imaginary and the real part are infinity. Okay, and just by seeing the sign, I know they are in the second quadrant. Okay, that's why the phase is equal to plus 180 degree. Okay, so any doubt in this question? Okay, so let's go to the next question. As frequency is varied from 0 to infinity, the Nyquist plot of this is a semicircle with radius 1. So we have already seen the Nyquist plot for this type of answer function. Okay, so let's again do it. Same thing we will do it. What we have to find out? Radius we have to find out. Okay, quickly I will find out. Okay, someone's mic is on. Okay, can you turn off the mic, please? I think some noise is coming. Okay, let's so find the real and imaginary part. What we do? So first it is 20 minus 2 j omega plus 10 j omega, and this is again minus minus plus omega square, 10 square plus omega square. Okay, so omega square plus 20 by omega square plus 10 square. Okay, this is the real part, and imaginary part is plus this one. Okay, so real part is so you can see it will be always positive, right? So in the previous question, like when I have written out real and imaginary part, so I was talking about like after omega equal to root 2, the real part will be negative, right? So you can see from here also, okay? So after, so these frequencies are like omega greater than root 2, okay? That's why the real part is always negative. Okay? So this conclusion already we have derived when we are just writing out real and imaginary part. Okay? So here also real part is always positive because omega square. Anyway, omega is positive. And what is the imaginary part? This one. It will be also positive. Okay, because omega is positive, 0 to infinity. Okay, so what is the magnitude? It will be omega square plus 2 square and omega square plus 10 square. Okay, so I'm writing the magnitude by seeing this. Okay, you can write the reals, root of reals, part square plus imaginary part, but you'll end up with this. Okay, and the phase is, so the phase is omega by 2 minus tan inverse of omega by 10. Okay, this is the phase. I think I'm writing it correctly. Correct. So let's find the values. Okay. Okay. So here we'll also find at 2 and 10. So if you see corner frequencies, you can see from the numerator it's 2 and from the denominator it's 10. Okay. So let's find out. So omega real part we have. We also want to find out the imaginary part. So at omega equal to 0, okay, what is the real part? Omega square plus 20 divided by omega square plus 10 square. So omega is equal to 0, you will get 20 by 10 square. So 20 by 100 you will get, so 0.2. Okay. 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 So 0.2 imaginary part is 8 into omega by denominator. Okay. So 8 into 0. You get 0. And magnitude you'll get 0.2, right? Imaginary part is equal to 0. So what is the angle you'll get? Again, omega is equal to 0. So tan inverse of 0, you'll get 0. Okay. So let's find out at 2. Omega is equal to 2. What is the value? So what you will get? Real part, what you will get? If you put, so it will be 204 by how much you will get? 104, right? Omega is equal to 2. So omega square is equal to 4. So numerator is 20, it is okay. Okay, 20 plus 4. And the denominator is 10 square, which is 100, plus 4 square in 04. So what is that value you will get? So 24 divided by 104. So you'll get 0.23. Correct?
8 by 104.
What happened?
Why 24, sir? Omega equal to 2.
Omega is equal to 24.
4 plus 4, 8.
Okay. Which value you're saying? Okay, imaginary part.
Part 104. Imaginary part.
One second.
Imaginary part.
So for omega equal to 2, what is the real part you're getting?
8 by 104. Root of 8 by 104.
Root of 8 by 104.
Hmm.
Okay. You're saying the magnitude. Okay. So
Okay.
first, let's find the imaginary part. Okay. So it's like 8 into 2 by 104. It's like 16 by 104. Okay. So 16 by 104. So what is the value you'll get?
2.15.
Correct. So I'm writing 0.15. Okay. So you're saying what was the value of the magnitude you'll get then? So it's, can you tell me the magnitude? You can do this also, 0.23 square plus 0.15 square. So 0.27, okay, something like that.
Yes.
Okay. So what is the angle? This is very crucial. Okay, let's find the angle. So find out this tan inverse of omega is 2 by 2. 2 by 2 is again 1 minus tan inverse of 1 by 10. Okay, so it should be 45 minus, what is tan inverse of 1 by 10?
Tan
If I,
inverse of 2 by 10.
so I think it will get 7.1, 5.71. Yeah, correct. So this is, sorry, this is 2 by 10. So to modify this, so 2 by 10. Okay. 11.30 is this value. Okay. So what is this? 33.6 or 33.7? Okay, I'm getting this. So at, let's take other point where omega is equal to, so other corner frequency is 10. Okay, so here let's take 10. Okay, this is just let's see. So what you'll get at 10? Real part 10 square plus 20, which is 120. And if you see the denominator, 100 plus 100, 200. Okay,
0.6.
just 0.6. Okay, so what is the imaginary part? 8 into 10, 80 by 200. So I think 0.4, right?
0.4.
So what is the magnitude? Root of 0.6 square plus root of 0.4 square. 36 plus 16. How much you are getting?
0.72.
0.72, correct. Okay, so if you find the angle in this case, okay, so just 10 by 2, okay, minus tan inverse of 1, right? Omega is 10, 10 by 10 is 1. So you try to find this.
The same, so 33.7.
Correct, so you'll get 33.7, exactly same. So let's find at the fourth point, which is at infinity. So at infinity, let's see what is the real part. So what is real part here? So you'll get 20 by 10 square. Point 2 again, I think. Okay, you have to find this. Okay, emit omega 10 to infinity, omega square plus 10, omega square plus 10 square. Okay, so what you used to do, this is what infinity by infinity term used to differentiate it, right? So you'll get 2 omega. Okay, 2 omega by 2 omega. Okay, so again, what is this? This is equal to 1, right?
Where omega square plus 2 square is.
Which one?
The numerators.
Numerator, what I will get? I'll get 2 omega. Okay, okay, yeah. I think so. I'm getting like 2 omega itself, right? If you differentiate omega
Yes.
square, it is 2 omega, right? So this is in this form, right? So I can get, this is the value I'll get is L hospital rule. You can apply differentiate numerator and denominator. You'll get 1, right? So the magnitude is equal to 1. Okay. So this is the real part. What is the imaginary part? So imaginary part, what you're getting is 1 by infinity. Okay. So if you see, so let me write it clearly. So this is the real part. Okay. So if you take imaginary part, what you want to find out is 8 omega into omega square plus 10 square, if I'm correct. Okay. So here, just you're neglecting it. Okay. Or directly you can put the limits. Okay. So what you used to do, to take omega square common. Okay. It is like 1 plus 10 square by omega square. Okay. Okay. So this is, now you put the limit, what you will get, 8 by omega, 8 is equal to 0. Sorry, this is infinity. Okay. Imaginary part is also is equal to 0. Magnitude is 1. And let's see what is the angle. So what you are getting, tan inverse of, because if you put omega equal to infinity, you'll get 90 degree minus 90 degree, right? You're getting 0. Okay. So let's again review for omega equal to infinity what we have done. Okay, so if you see the real part is this. Okay, omega square plus 10 by omega square plus 10 square. Okay, so we want to find at omega equal to infinity, not 0. Okay, so this we can apply the rules. Okay, L'Hospital rule. Okay, so we just differentiate 2 omega. If you differentiate the numerator, you will get 2 omega. If you differentiate the denominator, you will get 2 omega. And constant differentiation of constant is equal to 0. Okay, so you'll get 2 omega by 2 omega. That is equal to 1. Okay, so real part is equal to 1. And if you see the imaginary part, it is 8 omega omega square plus 10 square. Okay, if you put the limit, you will get 0. So that's why real part is 1, imaginary is equal to 0. And if you see the magnitude, real root of real part square plus imaginary part square is equal to 1. Okay, and if you see the phase and just put omega equal to infinity, which will be 90 minus 90 equal to 0. Okay, we have 4 points. So again, so I wanted to convey something, some observation. That's why we have calculated additionally for omega equal to 2 and omega equal to 10. So phase we are getting same. Let's see. Let's first draw the So this is real, this is imaginary, and this is G of S plane. Okay. So we first point at omega equal to 0, we have 0.2. Okay. Imaginary part is equal to 0. This is 0.2. Okay. And the angle is equal to 0. And the other points are 2 and 10. Okay. So they have different magnitude. And other last point is infinity. And at infinity, I am getting real part equal to 1, imaginary is 0, and again the angle is also 0. So this is 1. Okay. So already in the question they have said it's a semicircle. Okay. So how the semicircle will look like? It's not looking like semicircle. Okay. Okay. At least this is a semicircle. Okay. And we wanted to find out the radius. Okay. So let's first finish this question. Okay. Additionally, we'll see the points. So radius is like, okay, this is the diameter, right? So let me just see what is the diameter here. This is
0.4.
correct. So this is 0.8. Total diameter is 0.8, and the radius will be equal to. So what is the radius? This will be the radius, which will be 0.4. Okay, this is 0.8. Radius will be 0.4. Okay, there it finishes the question. Okay, that is fine. Okay, but we have additionally calculated two points, right, at omega equal to 2 and 10. Okay, so let's see. And interestingly, what we can say is angle is same. Okay, angle is same in this case, 33.7. So let me say what are those points. Okay, so if you see, so these 2 points. Okay, so this is 33.7 degree. Okay, so this is at omega equal to 10, and this is at omega equal to uh, omega equal to 2. And if you see the magnitude also, what you will observe is at omega equal to 2 you will have 0.27, and at omega equal to 10 you will have 0.72. You can see the magnitude also, right? From this graphical representation you can see at omega equal to 10 it has more magnitude. Okay, because magnitude is what. So let me show. So this is one magnitude at omega equal to 2, and the other magnitude is this. So you can see at omega equal to 10 the magnitude is greater as compared to omega equal to 2. Okay, these 2 points I wanted to show you. Okay, and okay, let's go to the next question because it's related to this graph. Okay, so in the next question it is asking the maximum phase in sinusoidal transfer function. So let's copy this, and we'll be using this Nyquist plot to get the maximum phase. Okay, so this we know. Okay, so let me clear these things. So what is the maximum phase? Maximum phase is this one, this point somewhere. Okay, so this is not a proper semicircle. Let me try to draw a semicircle. Okay, okay, so the maximum, so this point, okay, so this point, okay, Okay, it's not clear. Once again, we'll take this point. Okay, this point has the maximum phase, right? You can see this angle we are talking about. If you see all the points on the curve, this makes the maximum angle, right, for that particular point. Okay, and we have to find this maximum angle. Okay, okay, this is related to question. Okay, so you have to find this angle, right? And also we know it's a tangent to this semicircle, and this is 90 degree. So it's not clear, but this angle will be 90 degree. Okay, so you know, any semicircle, if you draw any circle you draw. So I'm not able to draw a circle. Okay, let's plot any circle, and if you draw any tangent. Okay, so this is the center. So you know it makes angle of 90 degree. Okay, this property we are using here. So this is 90 degree. Okay, so it's not like clear, but it is 90 degree. Okay, so we have to find the angle. Okay, so clear radius and all. So we know the radius of this semicircle is equal to 0.4. Okay, so we wanted, we know what is this. This is the center. Okay, some crucial points. So this distance is how much? So 0.4 plus 0.2, so it's 0.6. Okay, and this is the radius, right? This is the center. Okay, so which is equal to 0.4. Okay, so now can we find out the angle? So it's like sine of theta you're finding out, which is equal to 0.4 by 0.6, and theta is what? Sine inverse of 0.4 by 0.6. Can you find out 2 by 3 sine inverse of 2 by 3?
41.8 degrees.
Correct. So you'll get 41.8 degrees. Okay. So what is the center here in this Nyquist plot? This is equal to 0.6. Okay. This point is 0.6. Okay. So everyone is getting like how we are calculating the maximum phase in this case. Okay. So we see that this point. Okay. So let me mark that point as point A. Okay. So if you see from the origin, okay, you see at any point in that semicircle, the point A is making the largest angle, okay, or the maximum angle. And what we do, we just make a tangent to that point, okay, and calculate the angle. Okay, and the angle is coming out to be 41.8. So next question is also related to s plus 2, s plus 10. Okay, so we have drawn for s plus 2 and s plus 10. Okay, so last question is, so as frequency is varied from 0 to infinity, the Nyquist plot of s plus 2 and s plus 10 would always lie in first quadrant. Okay, so we have drawn the Nyquist plot. So this is the Nyquist plot, and what can we see? So it's always lying in the first quadrant. Okay. Okay. So any doubt in this question? In the previous question, why point A is making the maximum angle? Okay, you can see. and previous question we have drawn the Nyquist plot. Okay, so we at omega equal to 2 and omega equal to 10, we are getting the same magnitude of same phase. Okay, it's very interesting. If you don't know the values at omega equal to 2 and omega equal to 10, okay, still we can plot the Nyquist plot, because in the question it's given that it's a semicircle. Okay, so we know okay, it will start from point 2 and again it will end at 1. Okay. Okay, any doubt for the any question that is discussed today? Okay, so mostly it's a Nyquist plots that we have covered. Okay, for the known functions. And Bode plot. Okay, so we'll cover more questions on this Bode plots. Okay, so I'll take one extra session, that is like after week 12. Okay, so 22 October. So I will be discussing questions. So any doubt for today's session? Okay, maybe time is up. Okay, so any other doubt? Okay, then no doubt. You're not having any doubt, so I'll close the session for today. So thank you for attending the session. So I'll meet you in the next session, which is on next Tuesday. Okay, please see the lectures for week 11. Okay, so it's very interesting, because you know analysis, you already know that time domain analysis. Now you know the frequency domain analysis, Bode plot and the Nyquist plot, and how we use this analysis to design the controller. Okay, that's what is the topic of discussion for the next week. So please do watch the lectures. Okay, then we will do the assignment questions. So thank you for attending the tutorial session. So good night.
Thank you, sir.